Check it out now, y'all.
nanoHUB-U, online instruction.
Hello, and welcome to nanoHUB-U's course on organic electronic devices. My name is Brian Baduris, and I'm in the School of Chemical Engineering at Purdue University. Throughout the time of this course, we're going to learn a lot about organic electronic devices, and today we're going to start that by learning about the materials that go into the devices. While we're not going to become experts in the chemistry of the organic electronic materials that we talk about, we do need to be able to develop some basic nomenclatures and basic chemical structures so that we can talk about how molecular design principles guide the operation and device design of things like flexible solar cells and flexible lighting apparatus. So at the beginning of each lecture, we'll go over what the lecture will cover and the concepts I hope that you take away from each one of these. In today's lecture, we'll talk about the chemical structures of organic semiconductors, the nomenclature of these organic semiconductors, how we think about designing these materials and how that design impacts how they operate in the actual devices that we'll learn about later in the course, and we'll talk about how to characterize the molecular weight of semiconductors that are polymers. So after this lecture, I hope that we're able to draw the chemical structures of organic semiconductors that are common both in the literature and in practice, and be able to name and recite the chemical names of materials that you have the chemical structure for. I hope that you'll be able to predict the relative properties of two organic semiconductors if you're given the molecular structure, and you should be able to calculate the molecular weight and the molecular weight distribution of polymers by the end of this lecture. Okay? Now this all comes back to the idea that we're going to implement these in the devices throughout the course. And one key aspect of organic electronics that's currently in commercial application is organic light emitting devices, or OLEDs. Okay? And you'll see that we'll use these in applications such as TVs, from Sony in this particular example. And these TVs are thin and lightweight. Okay? The thickness of the actual screen is only about the thickness of a credit card. We'll also talk about devices that are flexible. Here you see a bendable phone from Samsung. Okay? And we can even have organic electronic materials that allow us to have transparent displays. So here you can see on this picture right here that the entire device is transparent aside from the part of the device that's being lit up. Okay? And this is from a startup company called Polymer. The fact that we can use all of these devices and displays comes from the fact that we have designed the properties of the materials to be able to do this. The other key device aspect that we'll talk about in this course is organic photovoltaic devices, or polymer solar cells. These things have large area production, as you can see here. They're very amenable to portable applications, and they're also amenable to devices and designs where you want to have conformal coating of surfaces. So here we see a bus stop and San Francisco City Hall in the background, and there's actually a solar cell conformally coated on the top of this wavy bus structure. So by using molecular design principles and some of the semiconductors and polymers I'll show you in just a second, we're able to make all these kind of cool devices. Okay. How do we define an organic electronic material? Well, in this course, we're going to talk about materials that are primarily constructed of bonds containing carbon, hydrogen, and oxygen atoms. Okay? There may be other, what we'll call heteroatoms, or other species present, like boron, silicon, things of that nature, but the majority of the material will be carbon-based. Okay? While there's many different definitions for what an organic electronic material, in this course that's how we'll limit ourselves. In general, our organic semiconductors will have a lot of pi conjugated bonds. And I'll show you in just a second what that means. But if you recall from an organic chemistry class, that just means that we have single and double alternating carbon-carbon bonds. Okay? And the last thing we'll think about when we talk about organic semiconductors in this class is the idea that they're van der Waals solids. Okay? So they're bound together with covalent bonds as opposed to metallic or ionic bonds. Okay? And in these organic semiconductors, I'll show you three different examples. The first is where we have single crystals of the organic semiconductor. So here's an image from the Podzarov Research Group at Rutgers University. And what you see here is a semiconductor that's actually the size of roughly a 3 centimeter by 3 centimeter wafer. Okay? That's a single crystal of an organic semiconductor. We can also have organic semiconductors that are crystalline on the micro scale. Okay? Here we see a scale bar of roughly 1 micron, and we see that one of the crystallites of this pentacene thin film is on the order of 1 micron. We can even have texture at the nanometer level. So what I hope you see here is that by designing the materials in different ways, we're actually able to tailor the structure of the materials as well. Okay? So let's talk a little bit about how the chemical structure of some small molecule semiconductors look like. Okay? And here I've drawn the chemical structure of pentacene. Okay? And we have the acene there. That's when we have fused rings together like this. Okay? And penta comes because there's 5 of them. 4 and 5. Okay? Now in this nomenclature, I'll remind you that the point that I draw right here, any one of these points, corresponds to a carbon atom. Okay? The shorthand abbreviation is to use those as carbon atoms. And whenever I have a single line drawn, that is a single carbon-carbon bond. If I have 2 lines drawn like that, that's a carbon-carbon double bond. So what we see on this pentacene molecule is the fact that we have single bond, double bond, single bond, double bond, single bond, double bond throughout the material. That's what we'll refer to as pi conjugation throughout the course. And we'll find out that the higher we have a degree of pi conjugation, the more likely the material is to transport charge well. So in this pentacene molecule, you'll see that the entire molecule is conjugated. This makes it very rigid and fairly hard to dissolve in solution. So what we'll commonly do in this course, both for small molecules and polymers, is to add what we'll call solubilizing groups, or side chains. So in this case, we see that we have that same pentacene structure in the middle, but now we've added soluble side chains right here and right here. And that's what the TIPS comes from, okay? What that means chemically is beyond the scope of this course, but we'll see that that TIPS pentacene is now soluble in organic solvents, while the pentacene itself is not very soluble. Okay? In addition to pentacene derivatives, we'll also have things like rubrene. Here we have 4 materials all hooked together. And then we'll also have phthalocyanines, okay? And this will have mostly carbon-carbon bonds, a little bit of nitrogen throughout, and right here where I've drawn the M, that'll be a metal atom, so either copper or zinc usually. So we'll talk about CuPC for copper phthalocyanide and ZnCP for the zinc derivative. Now you'll notice that I've labeled these in red and I've called them P-type or hole transporting materials. What does that mean? Well, just like you may remember from a solid state physics course, okay, we can either preferentially transport electrons in our materials or the opposite of an electron, a hole, the absence of an electron. And these materials, for reasons we'll get into throughout the course, prefer to transport holes as opposed to electrons. And we'll talk about why and how to measure that later on. Okay? So we have the P-type materials and we also have N-type organic semiconductors. The most common N-type organic semiconductor is Buckminster fullerene or C60 or a buckyball. Okay? And this is just 60 carbons all hooked together in a spherical structure that have alternating single and double carbon-carbon bonds. Okay? Just like TIPS pentacene, we can make C60 soluble by adding a solubilizing group. And when we do that, we get a molecule that we call PCBM. So very often we'll talk about PCBM as being a soluble fullerene derivative. The last type of N-type material I'd like you to be familiar with is something called PTCBI. Okay? And this material is also used commonly in a lot of organic electronic applications. You'll note that I've added 4 P-type materials and 3 N-type materials on this slide. And that was done by design. And that is generally because it's easier to find P-type organic semiconductors than N-type semiconductors. And the reason for that will be explained a little bit later on in this course, but keep in mind that a lot of times we'll see the same N-type materials over and over again, but we'll vary the P-type material. One thing that should be noted on these slides, they'll be consistent throughout the course, is this part right here that says further reading. Okay? In this further reading, I encourage you to go into there and dig deeper if you're interested in the particular subject. If for some reason it's not of that much interest to you, it will not be tested, not be quizzed, but I want you guys to be able to have an extra source to turn to in case you are interested in a particular subject. And this happens to be a very good review paper regarding small molecule organic semiconductors. We also have the other analog of the small molecule semiconductor is the polymeric organic semiconductor. And we'll talk quite a bit about these throughout the course as well. The first one I'll point your attention to is this PPV derivative. So in PPV, I'm talking about phenylvinylene. So this is a phenyl group right here, this 6-membered ring, and this is the vinyl group right here. Okay? So poly is the first P, phenylene is the second P, and the vinylene is the V in PPV. Okay? We put solubilizing groups. Here's the methyl group and the ethyl hexyl group on this chain. Okay? And those solubilizing side chains allow it to be dissolved into solution readily. Okay? So we'll talk about PPV derivatives a lot in this class. Another derivative we'll talk about a lot in this class is that of poly-3 alkyl thiophene. So this 5-membered ring is a thiophene. And the sulfur is the 1 position, this is the 2 position, and this is the 3 position right here. So it's 3, and this is an alkyl chain, so it's poly-3 alkyl thiophene, P3AT. And we'll have an entire lecture devoted to these materials because they've been one of the most often used materials in the organic electronic world. Okay? We also have more advanced P-type materials, and the two that I show here, I want to highlight 2 points. The first is that they contain thiophene-like units and phenyl units throughout. We have more fused thiophene, and fused phenyl units. And throughout the backbone, there's a large degree of conjugation, here and here. And there's also large side chains to make them soluble in solution. So I hope what you're starting to see in these materials is that we have a large degree of conjugation with solubilizing groups that don't have those repeating pi single and double bonds. And that allows us to get good charge transport, but also lets us print our materials so that we can have low-cost, flexible devices. Okay? And the last material I'd like to talk about is this polyethylene dioxythiophene doped with polystyrene sulfonate, P.PSS. So this is what happens when you combine a conjugated material, so this polythiophene with a side chain, with a non-conjugated material. But this material is very metallic, and it behaves almost like a traditional conducting species. Just like in the small molecule case, we have P-type materials shown here, but we also have N-type materials. Here we see that if we add cyano groups, these CN groups, we change it from transporting holes, as we did up here, to transporting electrons. Okay? We can also have ladder-type polymers and very complicated materials, as the PNDID2OD-T2 shows. And what I want to highlight again here is the fact that we have some P-type materials and we have some N-type materials, but we have many more P-type materials readily available for polymeric semiconductors as well. Okay? So how do we design these materials? Well, as I alluded to on the previous slide, generally we start with something that has a relatively conjugated backbone. So we'll draw that as a very rigid, thick line. And the idea behind that is if we have a lot of conjugation, a lot of these alternating single and double carbon-carbon bonds, okay, not only will that let the electron delocalize longer, which will increase charge transport, but it should increase our crystallinity of our thin films as well. Okay? In general, a higher degree of crystallinity will lead to a higher degree of order, which should be good for charge transport. So things we think about when we think about the backbone of the polymer chain is that if we have a higher molecular weight polymer chain, we should have a higher degree of crystallinity. If we keep all of the repeat units of the chain roughly the same size, we should have a higher degree of crystallinity. If we have fused rings, just like in that pentacene case, we should have a higher degree of crystallinity. And through all these things, we should be able to get higher charge transport. Now, in general, when we think of organic electronics, we think of solution processable materials, and that's where the side chains come into play. So once we have our rigid backbone, we then add on the flexible side chains. And these allow us to dissolve our materials in common solvents. Okay? And in general, the main purpose has always been to increase the solubility of the materials. But what we've started to find is that they can have secondary effects. And the first one is that they'll affect the thermal transitions of the materials because they affect the crystal properties of the materials. And in turn, that'll affect how they absorb light and how they transport charge. Okay? So when we're making these materials, and when we talk about how we utilize them in the devices, we need to think not just about the backbone of the material, but also about the side chains of the material. Here, let's take a case study, okay, to highlight this fact. So here we have poly-3-hexylthiophene, so P3HT. Here's our thiophene unit again. Okay. Here we have 1 carbon, 2 carbons, and then C4. So that's 4 plus 1 plus 2 is 6. So 6 is hexyl. Okay, so that's poly-3-hexylthiophene. One level up, we see that we have poly-3-dodecylthiophene. So again, we have 1, 2 plus 10 is 12, and dodecyl is the prefix for 12. So P3DD, dodecylthiophene. And then in the last case, we have poly-3-ethylhexylthiophene. So again, we have 1, 2, plus 4 is 6 carbons. So that's the hexyl, that's the H. And then we have 1, 2 side chains, ethyl. So ethylhexyl, so P3EHT. And what I've shown here is the X-ray diffraction or X-ray scattering pattern of these 3 different polymers. And we'll explain what all these peaks mean in future courses. But the one thing I want you to notice is these look fairly similar. So one might anticipate that this would allow them to have very similar structural and optoelectronic properties. It turns out to not be the case. In fact, we can see here that where these guys absorb light is somewhere in the visible spectrum. That's why we like to use them for solar cells, right? So we can see that both these guys, when they're dissolved in solution, they absorb light somewhere between 400 and 550 nanometers in wavelength. And if you recall from your introductory physics course, that makes these solutions orange. When we take them out of solution and make thin films out of them, the first thing that you notice is that the properties move from lower wavelengths to higher wavelengths is where we absorb. Now we're absorbing out past 600 nanometers. This is towards the infrared part of the spectrum. So this kind of transition is known as a red shift. And a lot of our polymers, when we take them from solution and put them in the solid state, they will red shift. And this has to do with increased order and increased crystallinity. You'll see that between those 3, their spectrum don't overlap at all when they move into the solid state. Okay? And we'll explain why later on in this course. But this is a point to highlight the fact that you need to be able to control the molecular structure very well if you ever have any chance of using these in things like solar cells. The last thing I'll point to is the fact that how quickly charges can move in them changes based on this structure. It changes over an order of magnitude between 10 to the negative 3 to 10 to the negative 4, so this is lower, based on the fact that we added 2 carbons to every repeat unit of this polymer chain. Okay? So the idea that this little 2-carbon branch can change these materials is a huge deal. And we'll explain how people go about designing those and how you can use them in your own studies. Okay? So if we're talking about polymers, one of the most important characteristics is the molecular weight of the polymer. And when I say molecular weight, that means how long is it? How many of those repeat units do I have hooked together to make my polymer chain? Okay, so let's take a few small examples. Okay, so here I'm going to call a repeat unit a blue ball, And in this particular chain of polymer I have 1, 2, 3, 4, 5, 6 balls. So we'll call that a 6-mer. There are 6 repeat units hooked together. In a very similar fashion, in my mixture of polymers that I've created, I can also have ones that have 10 repeat units, and I'm going to say that I have 2 of those. Okay? And I'm also going to say that I have a 16-mer that has 16 blue balls. Okay? So now we're thinking about this polymer. And if someone walked up to you and asked you what the molecular weight of hydrogen, diatomic hydrogen was, you would say H2, and each hydrogen has roughly 1 gram per mole. And you would say every mole of hydrogen, or every mass of hydrogen is 2 times 1, and the molecular weight of H2 is 2 grams per mole. Okay? But now we have this polymer. All the blue spheres are the exact same things. Okay? They're all the same. But now I have this mixture of them together in one pot. Some of them are 6 units long, some of them are 10, some of them are 16. How do we define a molecular weight? Well, one way we do that is the number average molecular weight, which I'll symbolize as M sub n. Okay? And the way we think about the number average molecular weight is much like you think about an average of, if you were to pick the average height of a group of 30 people. Okay? You would take all their heights, sum them all together, and then divide by the number of people in the room. And that's the number average height. So we'll talk about the number average molecular weight. And to get at that more rigorously, we'll assume that each one of these blue balls has a molecular weight of 100 grams per mole. And the molecular weight of a single repeat unit I'll call M naught. Okay? So that's the mass of a single repeat unit. Okay? And I know then that the molecular weight of one of these chains must just be the mass of one repeat unit, M naught, times how many of these there are. So this 6-mer then must just be M sub 6 equals 6 times 100 grams per mole, or that chain must be 600 grams per mole. In a similar way, the 10-mer must be 1,000 grams per mole, and the 16-mer must be 1,600 grams per mole. So each one of those now has a molecular weight. How do we average it? Well, the way we average it is to take the mole fraction. Okay? So we know that the mole fraction is the number of species I, for this case this would be 1, 2, or 1, divided by the total sum. So this would be 1 plus 1 plus 1 plus 1 is 4. Okay? So the mole fraction of 10-mers in this case is 2 over 4, or 50%. Okay? To get the number average molecular weight, we're just going to take that mole fraction and multiply by the molecular weight of the I-mer. Okay, the 6-mer, the 10-mer, the 16-mer. And if we do that, the math will reduce down to something where we say the molecular weight in number average terms must just be equal to the molecular weight of a single repeat unit times this summation, the length of the I-mer times the number of I-mers I have, divided by the total number of I-mers. Okay? So let's do an example calculation using these very simple 4 polymer chains. Okay? So I know that M naught is 100 grams per mole. Okay? And in my first case, I have 1 6-mer right here. I have 2 10-mers and 1 16-mer. And on the bottom, I have 1 plus 2 plus 1 is each one of my N sub i's. If I do that math out, I get that the number average molecular weight is 1,050 grams per mole. Okay? This is equivalent to reaching into a bag, picking out one of the repeat units, one of the chains at random, and figuring out which chain you would pick out. You could also think about picking out one of the repeat units at random. And if you pick out one of the repeat units at random, the bigger the chain is, the more likely you are to pick out one of those chains with one of those repeat units. We call that the weight average molecular weight because larger chains are now counted more. Okay? So we'll have the same set of 4 polymers, my 1 6-mer, my 2 10-mers, and my 1 16-mer. Okay? We're going to keep the same fact that the blue circle is equal to 100 grams per mole. Okay? And we're going to find that the molecular weight of one of these is still Mi, is just the number of number of circles times the molecular weight of one of those circles. But now we're going to define the weight fraction as I Ni over the summation of I Ni. Okay, before, remember, it was just Ni divided by summation Ni. So now we're weighting this weight fraction by the number of repeat units in each chain, symbolized by letter I. Okay. If I go through the exact same math in this case as I did before, what I'll end up finding is that my formula reduces down to M naught times the summation I squared over Ni divided by the summation I over Ni. So here we have an extra I term both in the numerator and the denominator. Okay. And through this, if we redo the calculation, we'll see that I have 100 stays the same, and we still have 1 6-mer, but now the 6 is squared. We still have 2 10-mers, but now the 10 is squared. And I still have 1 16-mer, but now the 16 is squared. And when I do this on the bottom, appropriately in the numerator or in the denominator, we find out the weight average molecular weight is 1171 grams per mole. So you'll see that MW, the weight average molecular weight, is greater than MN, the number average molecular weight. And this is true for all polymers that have any kind of molecular weight distribution at all, which is every polymer ever made. Okay. So how do we quantify this? What does this mean? How do I think about two different molecular weights? Well, we've come up in the polymer community with a term for this, and it's called the dispersity. And the dispersity measures the relative ratio of MW to MN. Okay? So if every polymer chain had exactly the same molecular weight, if they were all 10 mers, the dispersity would be 1. So the lower limit of D stroke is what we call that variable, is 1. The upper limit can be infinity if you have a very dispersed sample. Okay? But let's think about what that means in terms of real properties, things we're more used to. You can relate the dispersity to the standard deviation. So if I call the average molecular weight M sub n, the number average molecular weight, we can see from this equation that the standard deviation is just M sub n times D stroke minus 1 to the 1/2. So as D increases, D stroke increases, our standard deviation increases. And if D stroke goes to 1 in the ultimate limit, we have no standard deviation. Which makes sense because that means all the polymer chains are the exact same length. So there's no deviation from the average. Okay. So in this way, we can quantify molecular weights of polymers and dispersity of polymers to get at certain properties. And in our case, the things we'll be looking at is the fact that higher molecular weight and lower dispersity leads to increased crystallinity, and generally that leads to better charge transport properties when we put these into transistors, light-emitting diodes, and organic solar cells. Okay. So what we've covered today, the first thing I hope you've realized is that we need to think about our pi conjugation, the number of single and double bonds that we have throughout the device. We've shown some small molecule semiconductors that can form big crystals, and we've also shown some materials that separate on the nanoscale. Okay? We've also talked about the different kinds of polymers we want to use and how to characterize the molecular weight of these polymers. So we'll go back, look through the lecture, and I hope what we'll realize is the idea that it's very important to characterize the molecular properties of our materials before we start making devices. In our next lecture, we'll start talking about how to synthesize these materials, and we'll actually move on to a very special kind of materials, those poly-3-alkyl thiophene. Thank you, and I look forward to seeing you again at the next lecture.